show that the Broglie wavelength of an electron of mass m and charge E accelerating through a potential difference V is given by lambda equal to h over square root of 2m eV, which is also equal to 12.27 over square root of V Armstrong. This is the question I will be solving in this video. Okay? The first thing we'll have to write out here is the kinetic energy gained by the electron. The kinetic energy gained by electron is equal to 1 over 2 mv squared. That is the kinetic energy gained by the electron. The next thing I'm going to write out is the work done on electron. The work done on electron is equal to EV. Okay? Okay? Then, according to work energy principle, according to work energy principle, it says that energy is equal to work. That implies that the kinetic energy gained by the electron will be equal to work done on the electron. So I will equate these two expressions. I'll have 1 over 2 mv squared is equal to EV. Okay? Where m is the mass of the electron, v is the velocity of electron, E is the electron charge of electron, and this V is the potential difference. Okay, let's rearrange this expression. I'll have mv squared is equal to 2ev. Then multiply both sides by m, multiply both sides by m. I'll have m squared v squared equal to 2m ev. Remember that momentum P is equal to mv. Okay, so I have momentum here, right? So mv is momentum. Because of the square, I'm going to be having P squared, right? Which is equal to 2mev. Okay, so P, remove this squared, so it becomes square root on the right hand side. Then I have P is equal to square root of 2mev. Okay, that is what I will have now. Call this equation 1. Now let's write out the de Broglie wavelength using from de Broglie wavelength equation from de Broglie. Okay, which says that lambda is equal to h over p. This is de Broglie wavelength. This is the equation for de Broglie wavelength. The wavelength lambda is equal to Planck constant h all over momentum p, right? It can also be expressed as h over mv, right? Okay, we already have our p here in equation 1. Call this equation 2. We already have p as which is equal to square root of 2 mev. Then I'm going to substitute this value of p in place of p in equation 2. So substitute equation 1 in equation 2. I'm going to have lambda is equal to h over, okay, I'm putting this expression now in place of p over square root of 2 mev, right? So this is the Broglie wavelength. The Broglie wavelength lambda is equal to h which is Planck constant all over 2 multiplied by mass of the electron multiplied by charge of electron multiplied by what? The potential difference. So the first part of the question has just been completed, which is this part has just been completed. So he now said it is also equal to this expression 12.27 over square root of v Armstrong. Okay, let's go to that side now. Okay, this is our de Broglie wavelength for electron accelerating under a potential difference v. Okay, then Planck constant has the value of Planck constant is 6. We substitute the value, we substitute for Planck constant, we substitute for mass of electron, and we substitute for charge of electron. Okay, then we'll evaluate, then we'll have that value, which is that Planck constant is 6.67 times 10 raised to the power of minus 34 divided by square root of 2 times, because I have to here, multiply by mass of electron. Mass of electron is 9.1 times 10 raised power minus 31. Okay. Charge of electron charge is 1.6 times 10 raised to power minus 19 times v. Okay, I've substituted the values of Planck constant, mass of electron, and charge of electron. Then if you evaluate what you have here, you are going to have 12.27, okay, all over square root of v. You can see that the value of v was not given, so it's still going to be in the square root. So we have evaluate all these ones except v. So the value of v is still going to be in the square root. times 10 raised to the power of minus 10 meters. So this is what you are going to have. Okay, remember that 1 Armstrong is equal to 10 raised to the power of minus 10 meters. So I can substitute Armstrong in place of 10 raised to the power minus 10 meters here. So I will have, because Armstrong is the units used in the question, not meter. So I have to take it back to Armstrong. So I'm going to have 12 equal to 12.27 all over square root of V Armstrong. So this is how to derive it. So how to derive this wavelengths of electron accelerating through a potential difference V. Okay, I'll see you in my next video.